introduce Terry Tao, who is going to talk about a regularity lemma for definable sets over finite fields and expanding polynomials.
Okay, thank you. Thank you very much for this invitation. It feels a bit funny for me to be speaking at a conference on model theory and algebraic geometry because I am not a model theorist. I'm not an algebraic geometer. I do some number theory, but there's no number theory in this talk. My background is very much from a finitary sort of combinatorial perspective, and unfortunately I don't really speak the language of model theory. Everything I'll be talking about has a sort of translation into model theoretic language, but hopefully you'll see it better than I can. But anyway, so what we're talking about is regularity lemmas for graphs, for special types of graphs. And it's modeled on a very famous regularity lemma of Andrea Zamaretti. Which is a description of large, dense graphs. And it's the amazing fact that in principle, there are huge numbers of large, dense graphs out there. If you have n vertices, the number of graphs you can put on n vertices is about 2 to the n squared. But actually, if you are interested in sort of the usable statistics of these graphs, the space is much more compact. It's much smaller than you might first expect. There's a lot of structure, a lot of regularity to large graphs. So there are many ways to formulate this lemma, which I think he introduced initially in a paper in 1975, and then cleaned up in 1977. So here's one formulation. Okay, so I'll take the bipartite version. So we're going to have two vertex sets, V and W. These are finite sets. Okay, and I'll think of this as like a square. And my graph is just going to be a bipartite graph connecting V and W. So in other words, it's just a subset of V equals W. So it'll be just some funny subset. Okay, just an arbitrary subset, E, of V equals W. And V and W you should think of as being extremely large. And then you have some small parameter epsilon. And then with all this data, the conclusion of the regularity lemma is that no matter what E is, you can partition V into a finite number of pieces, V1 up to VA. You can partition W into a finite number of pieces. So you can partition V into finite pieces, W into finite number of pieces. Okay, and there's not too many pieces. A is bounded by something depending only on epsilon, and B is bounded by something depending only on epsilon. If you wanted to, you could make all these V's the same size and the W's the same size. I won't do that here. It's not so terribly important. And so then, such that most pairs are regular. So what most pairs means is that I'm going to allow for some pairs here to be bad. Okay, so there's going to be some sort of bad pairs. Okay. But these bad pairs will be small in the following sense, that if you add up the total area of all these rectangles, it's a small fraction of the whole. Okay, so there's some bad pairs which occupy about an epsilon fraction of this whole square here, or rectangle. But for all the other pairs, you take one of the good pairs, then the graph looks very, very regular. And so if you take a good pair, then there exists a density, Dij, which is a number between 0 and 1, such that, so if I blow up this pair here, so called Vi and Wj, the portion of the graph inside this pair is very uniformly distributed. Okay. It's uniformly distributed with density Dij. So the precise statement is that there's a density such that for any subset A in Vi and any subset B in Wj, so you take an A here and a B here, and you want to count how many points in E lie inside A cross B, then the number of points here is pretty much what you expect. So the expected number would be the total size of A cross B times the density. And this guess will be correct up to an error of epsilon times the size of this rectangle, Vi, Wj. Okay, So up to a small error, the number of the density of E in any box which is reasonably big. Yeah, so this estimate is not very interesting when A and B are small, because in that case this error term is bigger than this main term. But when A and B are pretty big, like they're bigger than, say, twice epsilon or something times this times the size of VI or WJ, for big A and B, sort of macroscopically, if you take a sufficiently broad scale, E has density dj, as far as you can tell. Okay, so no matter what E is, you can break up E into pieces, where some pieces are bad, but most pieces, things look very, very uniform. And this is an amazing theorem because E is completely arbitrary. It's just an arbitrary set. There's no assumptions on the set, just that it's a set. And also the conclusion holds for all sets A and B. There's also no assumptions on A and B. So it's an incredibly powerful theorem in graph theory. It's used all over the place. Maybe I'll give some examples to illustrate this lemma. So, for example, you could take a graph which is sort of finite rank type graph. Like I could, for example, split V into 2 pieces, W into 2 pieces, and I could have a graph that looks like this. Okay, that it's I take all the edges connecting V1 to W1, all the edges connecting V2 to W2, and none of the edges here and here. Okay, so for this graph, this is certainly not a regular graph in this sense. Okay, so this graph has density 1/2. Okay, so about half of the edges are occupied. But if you look at on the subrectangle, the density is 1. Okay, so the density is much bigger here than it is on the whole. So this graph is not regular in this sense. But if you partition V into these 2 pieces and W into these 2 pieces, then on each of these squares, the graph is regular. This is regular of density 1, density 0, density 0, density 1. Okay, that's a trivial example. And then so the opposite example is a random graph. If you take, if you look at V equals W and you just pick half the elements at random, then you can just use elementary probability to tell you that with very high probability, this graph will have density of pretty much 1/2, and it will be regular in the sense that if you fix epsilon and you let the number of vertices here get big, then the density in any sub-rectangle of reasonable size will also be about 1/2. And so this graph will be regular. And roughly speaking, the Zimmermann regularity lemma is the assertion that every graph is somehow a combination of these 2 examples. Okay, sort of a deterministic finite rank type object where the membership relation is determined only by this finite complexity vertex sets here, and then the randoms thing. Okay, and then you can have combinations. Like you could have a random graph in here of density 2/3, random graph of density 1/3, so forth. Now, why are there bad pairs? So the classic example that shows you that there's bad pairs is what combinatorials call a half graph, but I guess what you guys would call an ordering. Okay, so you let V, for example, be the numbers from 1 to n, and you just you connect I to j if I is less than j, or maybe I is bigger than j, I is less than j. Okay, so 1 here and 0 here. And this is a graph, but no matter how you partition it, you can partition it so that most of the cells you get are regular, but the ones on the diagonal will not be regular. So if I partition like this is a cell with density 1/2, but inside it I can find a fairly large subcell of density 1 and also a large subcell of density 0. So this little piece is not regular. So whenever you have whenever you can see the half graph inside your set, then you expect to get these bad pairs. Okay, but in some sense, this is the only obstruction. So there's this very nice recent paper of Maliaris and Shellac, which actually makes that precise, that says, roughly speaking, that if you have a graph which doesn't have subgraphs, big subgraphs that look like this, look like total orderings, which I guess in model theoretic language is an assertion of stability of this relation E, then you can eliminate the bad pairs and you can improve the regularity lemma. So there's a sort of philosophy in combinatorics that this lemma is very, very useful, but it's a bit too general. I mean, its strength is that it applies to every single graph and every single and so forth. But because it's so general, it doesn't always give you the strongest statement. And if you restrict to special types of sets, you can do better than this lemma. So I wanted to talk about one. So there's several sort of ways to improve the regularity lemma if you make more assumptions on E, or if you change the format a little bit. So the precise lemma I want to state is what we call the algebraic regularity lemma. So it's a similar statement, except that everything is now defined over a finite field. So we will pick a finite field, and you should think of it as being a large finite field. This is a rather steady statement for a small finite field. Take a large finite field, and now V and W are finite sets which are defined over F. Now, this is also a silly statement because over any finite field, any finite set is definable, and that's all the finite sets are the only things you have. So if you want to make this meaningful, you need a complexity bound. Okay. Okay, so we look at definable sets that are definable with complexity less than m. So what that means is that V, for example, is contained inside F to some dimension, and D is at most m, and it's defined by some predicate. Okay, so I guess an affine definable set. Okay, and I want this predicate to have length at most m. Okay, if you don't like complexity bounds, you can pass to a pseudo-finite setting and work with a pseudo-finite field, and then V and W would just be definable sets with no complexity bound. And there's an equivalent way to think about that. You just take an ultra product. We use compactness theorem. So I come from combinatorics. This is that I like to see everything finite. Okay, but if you don't like finite things, you just replace every finite by pseudo-finite and ignore complexity in everything that I say. Okay, so take some definable sets with some complexity bound. So, for example, algebraic varieties over F with bounded degree. Take a subset of V cross W, also definable with complexity bounded. Actually, well, it doesn't really matter. We've got C. I'll use M somewhere else. Okay. All right, so those are my data, and the conclusion is that given any definable sets, I can split up V into pieces. Where the number of pieces is not too big. It's bounded by a quantity depending only on this complexity. All these pieces are also fairly big in themselves, so this is a minor technical thing, but usually these are themselves pretty big. So no small pieces here. In fact, actually this implies this. It's almost the same thing. What else? Oh yeah, each of these pieces are themselves definable. And unlike the ordinary regularity lemma where there's some bad pairs, here there are no bad pairs. All pairs are good. And then for all I and j, all I from 1 to a, or j from 1 to a, and then for any set A in Vi, any set B in Vj, for all I 1 to A and 1 to B, there exists some density between 0 and 1, such that, again, this picture happens, that the graph inside every single cell has a certain density, so that the size of E inside A cross B is close to what it should be, up to a small error, and the error is actually now pretty good. So here we just had an epsilon, which you can make small, but the smaller you make it, the bigger you have to make the size of the partition, which is annoying. But here there's a universal, I guess, well, okay, there's a constant or something like it, but there's a minus 1/4. The error is actually, it depends only on the field size. So as you make the field bigger, you automatically get better and better errors, but you don't need to increase the number of cells in your partition. Or if you like, if you take a pseudo-finite field, then you just have a finite number of cells in your partition, but then you get this sort of infinitesimal error term. Okay, so you have this. This is for all A and B. So so you have a stronger hypothesis in that you need definability everywhere you only work with definable sets, but now you get all pairs good, and you get a much better regularity bound here. Oh, and you also get this extra thing which actually turns out to be useful in applications, is that the cells themselves are also inherit definability, which turns out to be quite useful. So let me illustrate this with 2 examples. A simple example of a definable set is just the affine line, f itself. And so let me just give you 2 examples of density 1/2 graphs. Okay, so E1, for example, one graph is just going to set up all v comma w squared such that v times w is a quadratic residue. So v times w is a quadratic residue. Okay, it's a square of something in F. Okay, so this is clearly a definable set of length, 7 or something, complexity 7. So what does this set look like? Well, you can split up the affine line into quadratic residues and quadratic non-residues. There's also 0, but 0 is so tiny. Let me just ignore 0. This graph just looks like something like this. Okay? If you want v times w to be quadratic residue, you either need v and w to both be quadratic residues or v and w to both not be quadratic residues. Okay? Or there's a 0 case, which doesn't really make a difference. Okay? And so here you just have to partition your line into 2 pieces: the quadratic residues and the quadratic non-residues, which are definable sets. And then you get these 4 blocks, and on each block you've got a fixed density 1 or 0. Okay? So that's a simple example. Another example is what's called the Paley graph. Which is also a Cayley graph, but anyway, okay, it's Paley graph. It's the set of all numbers whose difference is a quadratic residue rather than the product. Okay? So this is another graph with density 1/2. What it looks like is that every row looks like some shift of the quadratic residues. You take the quadratic residues, which here I drew as an interval, but actually it doesn't look like an interval. As quadratic residues are spread out, sort of uniformly across the field, and you sort of keep translating them. Okay, and this is an example of a graph which is actually quite regular. This is density 1/2, and pretty much any big rectangle inside this graph will also have density 1/2. And the error is actually, it's almost as good as f minus 1/4. If you actually work it out, it's about f minus 1/2 is the error. There's a nice computation using Fourier analysis and Gauss sums, which I won't do here. And so this lemma is saying that somehow every definable graph looks like a combination of these 2 examples. Okay, so instead of having, you have to split up your definable sets into finite many pieces, and on each piece you put it in something that looks like this, with a bit of different densities on each block, and that's all there is. Okay, and you don't see the finite, and you don't see the half graph. Okay, because you can't define this in bounded complexity. Okay, that if you want to define a total ordering in a finite field, you can do it set theoretically, but if you wanted to do it algebraically, you need a huge complexity. Complexity grows with the field size. In fact, I guess this lemma proves that statement, in fact. But I guess, you could also argue using stability of finite fields or something, pseudo-finite fields, to prove that particular claim. Okay, yeah, but these are the only examples. Okay, maybe I'll talk about the proofs later, but maybe I'll just mention a quick, this lemma, I proved a special case of this lemma last year, where I proved this lemma on an additional hypothesis where the characteristic of the field was large. I needed that because I suck at algebraic geometry, basically. But then later, Sarchenko, also Khrushchevsky, independently, observed that actually you can just use stability theory. So I should have mentioned, what I used in this proof was I used, first of all, the theory of definable sets over pseudo-finite fields, which was worked out ages ago by Chatsidakis and Dries McIntyre. And then I used the Italo fundamental group. Properties of the Italo fundamental group. And as I said, I only understand this group in characteristic 0, which is why I needed to have this, this restriction here. Okay, but then Zachenko and Hrushevsky removed this hypothesis. Okay, so they can do all fields, all finite fields. So they basically, again, they use the Shetzer-Dark expanded Rice-McIntyre stuff, and then just some stability theory. Okay. And then later on, I found a third proof, which also was for all fields, which again, again we have to use this this basic description of definable sets, and actually just some spectral theory. Okay. Maybe I should also mention that in all three proofs we also use. I'll mention this. Okay. In all three proofs we also use the Cauchy-Schwarz inequality. I should say this because I really, for a combinatorialist, this is sort of obvious that whenever you do something like this, you have to use Cauchy-Schwarz. But it's somehow it's a tool which is very modest in looking, but it's incredibly essential because what Cauchy-Schwarz can do for you is that it can make statements about arbitrary sets like A and B, and by using the Cauchy-Schwarz inequality, you can control things about arbitrary sets in terms of estimates involving special sets, like definable sets. And so you always have to use Cauchy-Schwarz. You sort of can't get around it. But you have to use other stuff too. You can't just use Cauchy-Schwarz again. All right, but I just want to mention that. Okay, so maybe. Okay, so I'll talk about the proofs in a little bit, but I'll just mention quickly the applications. So far there's basically just one application of this lemma, but I really hope there's going to be more. So my motivation for this lemma was to understand expanding polynomials. Okay, so the setup is as follows. We have some large finite field. And we have some polynomial of two variables in the finite field, okay, and bounded degree. Okay, so the question is, when is P expanding? Now, expanding is sort of I'm being vague here because unfortunately there's about 6 different definitions of expansion and they're not compatible. But expanding roughly means that if you take some large sets of F, but not too large, large but not too large. So they're not all of F, okay. But not trivial either, okay. Then you want P of A comma B, which I just mean P of A comma B, where A is an A, B and B. I want this to be much larger than either A or B. Okay, so if you take 2 sets, you put them as input as polynomial, and what should come out should be bigger than what came in. And if that happens, you say that you're an expanding polynomial. Now, this is not a precise definition because you have to specify what large means and what all these terms mean. And depending on how you specify them, the notion of strong expanders and weak expanders. Sometimes you want A and B to be the same, then you have symmetric expanders. Let me just gloss over all that. Okay, so this is sort of the general concept of some polynomials you expect to expand, but they're somehow very mixing. That if you stick in large sets, you should get back even larger sets. But some are not. So before I talk about expanding polynomials, I can give examples of polynomials that are not expanding. So, for example, the addition map is not an expander. Because if you set A to be like an arithmetic progression, so suppose F is the field of P elements, and A is just the numbers from 1 to, say, P over 10, okay, and B is also 1 from P to P over 10. Then if you just add those 2 sets together, they only become twice as big, okay? It's these are approximate groups, okay? And so addition is because of arithmetic progressions, addition is not an expander map. And for similar reasons, the multiplication is not an expanding polynomial because of geometric progressions. You can stick in 2 geometric progressions inside this polynomial, and you get back a geometric progression of about twice the length only. So you don't get large expansion there. You can mess with the examples a little bit, so a bit more generally. Rather than x plus y, I can take maybe f of x plus g of y, where f and g are polynomials. This is also not an expander because you can take A to be the inverse image of a progression, arithmetic progression under F, and B to be the inverse image of an arithmetic progression under G, and this will also not be expanding. And I could even stick another polynomial over here, and this will also not be an expanding polynomial. Okay, so this is basically just a disguised version of the addition map. And similarly, you have this disguised version of the multiplication map. And these are not expanding polynomials. And basically what this lemma implies, with a slight bit of extra work, is that those are the only examples. Okay. So, so if P is bounded degree, okay, and not of these two forms. Okay, so these are very special polynomials. Most polynomials don't look like this. So if you write down a random polynomial in two variables, you will not be able to write it in either of these two forms. Okay, so not of any of these two forms. Then you're an expander in the following sense. Then if A and B are big enough, and big enough turns out, after a lot of Cauchy-Schwarz, to be bigger than f minus 1/16th, then P of AB is always at least bigger than constant times f. And this constant depends only on the degree of P. So you can have sets that are somewhat big. So getting close to, so of dimension close to 1, but it can be somewhat 1/16th away from 1. But you stick in this polynomial, and it will expand to be a full dimension, basically. Okay, so this basically gives you a description of which polynomials are expanders, at least in the regime of large sets. There's a lot going on for small sets, which is very interesting. You need some restriction because if you allow A and B to be of size f1/2 or less, then subfields of f start becoming a real problem because it could be that A and B are subfields, and P is defined as a subfield, and those aren't expanding too. And so there's this whole extra layer of complexity which really we don't understand, except for very special polynomials. But for arbitrary polynomials, we don't understand what's going on yet. Okay, but for very large sets, then that's the regime in which this lemma is useful, because this conclusion is useful when A and B are large. It's not so useful when A and B are small. So I won't talk much about how this lemma implies this this proposition. Well, maybe I'll just talk a little bit. So the way basically the way you hope to control something like this is that you start looking at the graph of P. Okay, so you look at the graph of P, which is some subset of F3. Okay, so this is sort of a surface. In fact, it is a surface in F3, and you start intersecting this with Cartesian products. Okay, so you take three sets A, B, and C, and you start intersecting this surface with these sets, and getting bounds like this corresponds somehow to getting bounds on this sort of expression. If you can prove that this graph is somehow sufficiently uniformly distributed that the density inside every one of these cubes is exactly what you expect it to be, then you can prove something like this. Okay, so there's some combinatorial manipulations that lead you to start studying this sort of object. Okay, but this turns out to not be so good because this graph, it's a subset of F3, but it's a very sparse graph. It's dimension 2 inside a three-dimensional set. It's not yet within the range of these sort of regularity lemmas, which really only cover sets of dimension really close to 4. So you pull out this Cauchy-Schwarz magic tool a few times. And the reason, it's because of the Cauchy-Schwarz that this 1/4 shrunk to 1/16. But you can manipulate this problem into an equivalent problem, basically involving not this set, but a slightly different set. So in fact, you have to use Cauchy-Schwarz twice. Okay, so rather than look at the graph of F of P, which is a two-dimensional surface inside 3 dimensions, you look at this sort of, it's like a graph of P, but it's a variant. So the thing is that this is a 4-dimensional object inside F4. you got 4 parameters, and you got 4, and you limit at F4. And what Cauchy-Schwarz tells you is that if you understand the distribution properties of this object, like you understand how this intersects, A equals B equals C equals D, this will give you some information as to how this set intersects this guy. So there's some Cauchy-Schwarz which I'm not going to present to you here. And so you can apply this lemma, and things work great so long as this set really is 4-dimensional. So for most polynomials P, if you take a generic polynomial P and you apply this map, so you can think of this as a map from F4 to F4. Usually it's a dominant map. The image will basically still be a very big piece of F4. And then this theory applies. But there are a few P's for which there's a collapse of dimension. Okay? What P's are like this? For example, the addition map, okay? A plus B, okay? Because A plus B prime, A prime plus B, and A prime plus B prime have a constraint that this minus this plus this is 0. Okay, so if P is the addition map, this collapses to a 3-dimensional space. And if P is the multiplication map, it also collapses to a 3-dimensional space. And if P is one of those two guys there, then it collapses to a 3-dimensional space. And so there is a lemma that those are the only P's that do that. And it was I didn't realize it at the time, but that is actually a special case of Rutowski's group configuration theorem, which is ever so. So that was nice. Okay, so now this is an easy theorem, given the group configuration. So I could prove this only in large characteristic because I was using complex methods, Riemann surfaces and so forth. But now you can prove it in any characteristic. So basically the group configuration theorem nicely explains, that the only time you don't expand is if there's an algebraic group that's blocking you. Okay, in one dimension, the only algebraic groups are the additive groups and the multiplicative groups. There are also elliptic curve groups, of course, but because these are polynomials, they don't show up because their group law is rational. There's an analogous theorem for rationals, rather than functions rather than polynomials, and then you also have an elliptic curve option, which I will not write down here. Okay, so that's the application. So let me talk about the proofs of this regularity lemma. So the way I like to think about all these lemmas is that is in terms of the adjacency matrix. So you can think about the adjacency matrix of your graph. So that's just a function which is 1 on your graph and 0 outside your graph. Okay, so it's a matrix. It's a V by W matrix of 1s and 0s. You could also think of it as a linear operator. I come from an analyst background, so this I can also think of as a linear map from L2 of V to L2 of W. Okay, so you take vectors here from W, you multiply by this graph, and you get these operators. So I guess I'm going to call that T. Okay, and it's convenient to normalize L2 to its using a uniform probability measure on each of V and W. And these regularity lemmas are actually, you can think of as assertions of compactness of operators. So an operator between two Hilbert spaces is compact if it can be approximated by finite rank operators. Given any epsilon, you can write your operator as a finite rank operator plus an error whose operator norm is less than epsilon. This is what it means to be compact operator. And these lemmas are essentially assertions of compactness. See, basically, what the Zimmermann regularity lemma is telling you, it's cheating a little bit, actually cheating a lot, but it tells you that any matrix, any operator coming from a 0-1 matrix can be written as a bounded rank operator, finite rank operator. Okay, plus an error which is small in operator norm. This is cheating. I'm cheating a bit. This is not quite the content of the regularity lemma, but it's very much in the same spirit. The bounded rank approximation is basically what you get when you take your original of E, you subdivide it according to the regularity lemma, and you just, instead of the 1s and 0s, you just stick in the densities. So if on every block you just stick in a constant number, and the number is the density of your of your graph, that is a finite rank operator, it only depends on if you want to evaluate it, it only depends on which one of these finite number pieces, or these bounded number pieces you live in. And this is the bounded rank piece. And if you subtract it off, what's left has small operator norm, and that's essentially what this bound, and also this bound is saying. I'm cheating a bit. Actually, small operator norm is not quite enough to get you this unless you define small properly. But very roughly speaking, these regularity lemmas are assertions. They're compactness assertions. And yeah, in analysis, they correspond actually to the statement that every Volterra integral operator is a compact operator. Okay, so and the algebraic regularity lemma is also very much in the same spirit, that every algebraic operator of this type can be represented as a bounded rank operator plus a small error. Now, where small means the operator norm is now as small as this f minus 1/4 thing, and the bounded rank part also has to be definable in some sense, so that you get this. Okay. All right. So the way you actually prove something like this, there's several ways you can try to do this. So the original proof of the regularity lemma is the Zimmeredi regularity lemma is very combinatorial. Roughly speaking, the way you originally prove the lemma is just a combinatorial greedy algorithm that you start with your original v cross w, and you'll set here, and you ask, is your graph already regular? Does it already obey this property without any partitioning? And if that's the case, you're done. If it's not the case, then there's some rectangle here where there's some fluctuation, where E is denser or less dense than the whole. And so then you partition that into subpieces, and then you hope that this new partition now has the regularity you want. And if it doesn't, then there's some more density fluctuation, and you keep partitioning. And you hope that this process terminates. And you have to be a little bit careful to do it properly so that it does terminate, but you can actually do it this way. So that's very, very roughly speaking the strategy of proof of the ordinary regularity lemma. You can't make that work here so well because that kind of strategy can't, for many reasons. It certainly can't give you such a good bound here, but it also can't give you the definability of the pieces. Because these A and B are arbitrary, so the sets on which you have density fluctuation could just be completely arbitrary sets. So there are other proofs. One proof that I'm very fond of actually is a spectral proof where you view this operator as a linear operator between Hilbert spaces, and then you just apply the singular value decomposition, and you can write any such operator here as a bunch of singular values times rank 1 operators. Okay, so there is some singular value decomposition, and there's some easy bounds on. If you normalize things properly, these singular values are actually square summable. Basically, the sum of squares of the singular values turn out to be basically the sum of squares of these entries. It's the Frobenius norm, and if you normalize it properly, that's 1. So you have these singular values which are summable, so they decay to 0 quite fast. And then once you have the singular value decomposition, then actually it becomes quite obvious how you're supposed to split up your T. You just take all the large singular values and you put them into the bounded rank part, and you take all the small singular values and you put them into the small part. And so there's a spectral proof of, for example, of the Zimmeredi regularity lemma, which motivated my final proof of the algebraic regularity lemma. Okay, but then there's another proof. So another way to try to control, to get it splitting like this is a trick from harmonic analysis called the TT star method. But like so many methods in analysis, this is basically code for Cauchy-Schwarz. It's amazing how many methods in analysis are really just secretly a repackaging of Cauchy-Schwarz. But yeah, so what you do is that you take your operator T and you square it. Actually, the way you square it, you multiply by its adjoint. So you've got an adjoint operator which goes back the other way, and you take a square, which is something that maps L2 of V to itself. And it turns out that if you can show that the square has this decomposition, then there's a way of taking square roots and concluding that the T itself has a decomposition like this. And if you want to make that formal, you either use the singular value decomposition or use Cauchy-Schwarz. So let me not go through that. The reason you want to do that is that often in practice, T itself is a kind of yucky operator because it's got this unknown set here. But when you square it, it smooths it out. It's kind of like when you convolve, for example, if you take two measurable functions, complex set, and you convolve them, they become continuous. And that convolution smooths things out, and this squaring achieves a similar sort of effect. So you want to work with the square, because that's a general principle. Now, so far we haven't actually said anything that's specific to finite fields, so you have to do something. And so what we use is the theory of Chastonakis, Banandrais, and McIntyre. Everybody uses this. And so what this tells you, the main thing this tells you is it tells you how big definable sets are. And so the way I'm going to phrase it is that if you have a definable set, F, then the cardinality of V will always be some number times F to some integer plus an error. Definable F of complexity bound. Okay, and D is some natural number bounded by something, in fact bounded by C. Alpha is a rational number, okay, and the height, just the naive height, is bounded by some function of C, and it's positive. Okay, and the error term here depends only on C. Okay, so all definable sets have a dimension and a density. So for example, just the quadratic residues. The quadratic residues in F are a set with dimension 1 and density 1/2. Okay. Okay, so and I guess what the model theoretic terms, what this means that you can put a Kiesler measure on the definable sets, which always gives definable sets very rational values in a pseudo-finite setting. Okay. Okay, so this is the first thing, that there's a very restricted range of cardinalities that definable sets can have. So you can't have a definable set of cardinality root F, for example. For my first proof, where I was using the Tao-Farmano group, I needed a few more facts. The first fact is almost quantifier elimination. That in fact, every V, it's not quite an algebraic variety, but you can always write V as the image of the F points of a quadratic of an algebraic variety for some. Okay, so the picture is that there'll be some algebraic variety W, and there's okay, and then you've got some base variety like Fn or something, and you've got some algebraic map phi over here, and you just take all the F points here, and you map them down, and that's what definable sets look like. Okay, basically there's one quantifier that you need coming from this phi, the one existential quantifier, but other than that, it's basically an algebraic set, and this is an algebraic variety of complexity controlled, and this also is an algebraic map of complexity, regular map, and complexity is controlled. Okay, so for example, for the quadratic residues, you just take the parabola, s equals t squared. Okay, and you take the F points on this, and you just project it down. Okay, and that's your definable set. So every definable set is the image of the F points of a variety. So that's one thing I needed. Another thing you need is that these alpha and b's they're definable themselves. So that if instead of having one definable set, you have a whole family. If you have a definable family of definable sets indexed by some other definable set, then this alpha depends on W and this D depends on W, but they do so in a definable fashion. That there's only actually finitely many values that this alpha takes, and the set where alpha takes a specific value is again definable. Okay, so there's all right. So there's some technical things that you also need. Okay, but this is all been known for a long time, and it's actually fairly it's not so difficult. There's one non-trivial input, which is the Langevin inequality, which comes from the Riemann hypothesis for curves. But other than that, it's actually not so difficult. Oh, okay. And for my first proof, I needed one final fact, which is that in the case, okay, so this is This is a rational number in general, as you see in this quadratic residue example. But if V is itself, if you're taking the rational points of a variety, then alpha will be an integer. It's a natural number. And in fact, it's a specific natural number. Alpha is then the number of connected components. And D will be the dimension of W, if W is defined over F, I guess. Okay. And alpha will be the number of connected components, irreducible components, irreducible top dimensional components of W that are Frobenius invariant. Okay, so finite fields come with a Frobenius map, and some varieties get preserved by these and some don't, depending on whether they're actually defined over F or not. And so if you take a variety W, you break into components, the ones that are defined over F will give you a lot of points, and those that are not Frobenius invariant will give you very few points. Okay, so there's actually a formula, an algebraic geometry formula for this alpha, in the case that you actually define all. Okay, so the way I initially proved this lemma was that as I used the GT star method. So you start with the indicator function of your definable set. So that's Yaki. So you look at the square. And so what is this? This is a matrix with a lot of coefficients. And if you work it out, what the coefficients are is that you count how many V's. Yeah, so you've got V and W. And you've got this bipartite graph, E, connecting V and W to itself. And now you're basically counting length 2 paths. That's the combinatorial perspective. So you take W and W prime, you count how many V's there are which are joined. So the VW and V prime W, VW prime, both line E. Okay, if you work it out, this is what the square, the GT star of your matrix looks like. It's just counting length 2 paths. Okay, that doesn't look much better than what you started with. But if you know the fact that, so it's the cardinality of this thing. If you know the fact that, that your definable sets are coming from algebraic varieties, you can rewrite this. So E itself is coming, okay, the way you can think of E is that for every W, you've got a slice, which is a definable subset of V, which varies in a definable manner based on W. And so, and as I said, every definable set of a V you can think of as coming from some other variety, let's say U. So basically, for every W, there's a variety hanging above W. And you take the F points of these guys, and you push them down, and that is what the slice, that's what, say, EW is. That's what the one row of E looks like. And what this is the intersection between one row and another row. Okay, that's what this thing is. And so geometrically, what this thing is doing is that you've got a fixed base variety V. Okay, V is initially a definable set, but you can lift it to a variety. So you've got this base variety V. You've got a whole bunch of varieties which are lying above V, UW, UW prime. And it turns out you can normalize things that these have the same dimension. In fact, you can make them finite covers. You have to delete a small dimensional set, but they're usually generically finite covers. You've got these two finite covers of V, and then you take the tensor product, you take the relative fiber product, sorry. Okay, well, it's going to look exactly the same, but, this is a horrible picture. Yeah, I'll do it this way. Okay, so. Okay, you've got two lifts of V, and then you can take the pullback, the fiber product. Okay, and then you take the F points up here, and basically, after some manipulation, what you're basically doing is that what you're interested in you're interested in counting how many points can you find up here. That's not quite the same as how many points are in the image, but it's a very closely related object. So what you want to understand ultimately is the cardinality of fiber products for a finite field. And what you want in order to get this regularity lemma is that you want this splitting into a bounded rank piece plus a finite error. So what you want is that you actually want this to equal some constant times the dimension of V plus a lower order term. So what you want is that as W varies and W prime varies, so these are lifts of V that vary definably in W and W prime. And so as they vary, the geometry of this fiber product changes. Some components will be Frobenius invariant some of the time, but not for some values of W and W prime, and not for others. So they keep varying, and the number of times they vary, the number of components that are Frobenius invariant. That's going to be this integer here, C omega omega prime, C W W prime, and you want this guy to be bounded rank. So what that means is that you can partition W into a bounded number of pieces, such that on each of these, so that W cross W gets partitioned into a bounded number of these rectangles, and for each of these rectangles, this is a constant number. This is only true for generic W and W prime. You also have to exclude things like the diagonal W equals W prime is bad, and there's a couple of diagonals you have to exclude. But generically, you want a representation like this. And if you can do this, then you are done. And so the way I did this directly was basically by brute force algebraic geometry. Which for me, just meant looking up SGA4 and reading it. So the basic problem is that you want to count how many connected components of this variety here are Frobenius invariant. You can assume that the base here is connected. The only problem is coming from the lifts. And so it turns out that the number of components of this guy, which are Frobenius invariant, is described by several things. It's described by the fundamental group of V. It's described by the generic fiber of UW. Actually, it's described by how the fundamental group acts on the fiber of UW and also on the fiber of UW prime. And it also depends on how Frobenius acts on these fibers. Okay, so Frobenius acts on these fibers, the fundamental group acts on these fibers. This is the Tao fundamental group, of course. And it turns out that if you have all this data, you can compute what the number of components are here. Okay? And the tool you use is the Van Kampen theorem from topology, which you adapt to the Tao fundamental group, which is not so difficult. And so you have all this data, and what you need to show is that this data so it depends on W, it depends on W prime, but it depends in a finite rank, in a bounded rank fashion. It only depends on a bounded amount of information of W, and a bounded amount of information of W prime is all you need to prove this. And so I was able to do this by looking. So after reading a lot of SJ4, I found a theorem that says the fundamental group in characteristic 0 is always finitely generated. In the topological sense, in proof-finite topology. Okay, and this turns out to give you the finite rank stuff that you need. Okay, and this is false in finite characteristic, and so this is why I couldn't do anything in bounded characteristic. I could only do things when the characteristic went to infinity. But this is how I finish things off. Okay, but then it turns out that you don't actually need any of that stuff. So what Pillay, Starchenko, and Khrushchevsky observed is that what's going on here is actually a much more general. There's this problem. I think I erased it, but I was looking at. So the whole problem is to understand. You have this arbitrary graph G, and you're taking rows you're taking two different rows of your graph, and you're trying to understand their common intersection. And so I thought that you had to attack this with all this algebraic geometry, but it turns out you don't. Okay, you can think of this in a much more abstract setting. You just have a probability space and a whole family. You have a family of measurable subsets on the one hand. Let's say indexed by the integers, and another family of measurable subsets, and you just take the and you just look at these numbers. Okay, so for different, you take arbitrary sets of sequences of measurable sets, and you look at these sequences of numbers, how one set intersects another set. And there's this very nice general lemma of Khrushchevsky. It says there was basically no hypotheses, nothing to do with definability or anything. This quantity gives you stable relations. So the Yeah, if you given any number p, for example, the assertion that this is, let me say, strictly bigger than p, is it basically gives you a stable relation, no matter what E and F do. So the way I like to think of this, coming from a finite tree background, is the following statement: that if you have two numbers p and q between 0 and 1, and suppose you can find even just a finite number of sets here and a finite number of sets in your probability space, and you know that this measure EI intersect Fj is always bigger than p. Let's say for whenever I is bigger than j, but it's less than q for I less than j. So suppose there's some very finite tree instability in this relation, in that it's big, that it's defining for you an ordering on n elements. Then it turns out that this can only happen when n is bounded. This can only happen for bounded n, depending on p and q. Okay, that you can't have sequences of sets which are big on when I is bigger than j, whose intersection is big on one side and small on the other side. Okay, so this is just a measure theory lemma. Okay, the way Hrushevsky proved this, so you can first pass to use compactness. You pass to an infinite setting, and then you use some Ramsey theory to pull out some indiscernibles. You can make the EIs and FJs order indiscernibles from Ramsey theory. Then you apply Definetti's theorem on exchangeable processes. It's actually a variant of Definetti's theorem to make the order indiscernible sets that you got here actually completely indiscernible, and then you get a contradiction because these two things are certainly not exchangeable. So it is a very nice proof. Later on, I found a direct proof of this particular lemma. I mean, it's so simple. It had to have a direct proof. And it turns out that actually another way to do it is to use a nice classical fact from harmonic analysis called Hilbert's inequality. Okay, which is the statement that if you take the matrix 1 over 1 minus j, I minus j, so it's an n by n matrix. Okay, so it's 0 on the diagonal, and then everywhere else is 1 over 1 minus j. So positive up here and negative down here, and it's got this 1 over x singularity. This is a discrete Hilbert transform. Then this matrix turns out to be bounded. It has an upper norm which is bounded. In fact, it's even bounded by pi. It's a very nice inequality. One of the first. It's a very nice application for Fourier analysis. Okay. So what this tells you in particular is that if you sum 1 over I minus j, and you take any bounded sequence ai, any bounded sequence bj, okay, this is bounded by n times pi. Okay, these are bounded sequences. In particular, I can take the indicator function of ei of x and the indicator function of fj of x for any x, and this thing is bounded by n pi. You integrate this using the triangle inequality. Okay, and you get this inequality. But if you have this instability here, then when I minus j is positive, this is bigger than p, and when ij is negative, this is less than q. And you can sum this up, and this is bounded from below by n log n times q minus p. And if n is big enough, you get a contradiction. Okay, so you can actually use analysis to replace model theory if you sometimes. Okay, I think I'm pretty okay. So I'm out of time. Yeah. Okay. Yeah. So yeah, and I should say that so this is a general fact, but in the specific application you care about, the mu's always take rational values, and so you can actually leverage this to actually prove this theorem. Okay. And then I had a spectral proof, but I think I'm out of time, so I think I'll just stop here. Okay, thank you very much.